Hey, Honors Chemistry. It's Monday, April 13th, and here we are again. We're studying Chapter 17, page 532. So take a look at this little device, the Hoffman electrolysis apparatus. Do you see how that it's producing hydrogen and oxygen? Well, let's take some of that hydrogen as we've done before, and let's take a little bit of that and pop it. Okay, let's stick it in here. That's nice. It's in this nice little test tube. There's all kinds of oxygen available to it right there at the front doorstep. How come that hydrogen isn't naturally, spontaneously combusting? That's the question. We have to give it this thing called activation energy. So let's give it a little bit of activation energy. You ready? Oh, yeah. We got ourselves some water. It was water vapor, but it condensed into water droplets. You can see that right in there. All right, so we're going to go ahead and put that. I'm going to turn this thing around so I can talk to it and use the board at the same time. Did you get dizzy? I hope. The device is all set up. But I needed for you to be able to see that. Okay, there's my whiteboard, and here am I. Great. Let's go to page, now keep that in mind what you just saw. Let's go to page 530. On 530, it talks about homogeneous reaction. Do you see at the bottom of the page, right above main idea? I'm going to read that to you. The reaction between hydrogen gas and iodine gas or vapor to produce hydrogen iodide gas is an example of a homogeneous relationship or reaction. They're all gases. It's a reaction whose reactants and products must exist in a single phase. Now they call it states of matter, and sometimes they call it phases of matter. And so the gas phase, in this case, makes it homogeneous. So I'd give you that bit of information. Now back to page 532. The question is, how come when I had a test tube full of hydrogen, it didn't automatically combust? And the answer to that, even though it has a negative delta E change in energy, which makes it exothermic, and most reactions in nature are exothermic, it also has a huge delta G, gives free energy, and that is negative 237 kilojoules per mole, which means that it's spontaneous. Well, it's only spontaneous if you give it some activation energy. Is the log spontaneous? Does it continue to drive at room temperature? If you ignite it, it does, but you got to give it some activation energy and kind of get the rock rolling downhill before it continues to provide the energy that breaks the bonds. So the breaking of bonds is critical so that you can rearrange the atoms that are in between. You have to break the bonds that are between the atoms in order to rearrange the atoms with different bonds, and that would be different molecules. And so let's take this one right here, 2H2 plus O2. I'll put that on the board. Initially it's gas, but then at room temperature it becomes a liquid, as we've already discussed. Okay, so that's the equation. These are the reactants, and they are higher energy. Why are they higher energy? Because they are gases. This is a liquid. This is lower energy. And the reason is because these are in elements that are in free state. And this is a compound. And I already told you that when elements turn into a compound and bonds are formed like that, then it releases energy, and that's exothermic. In fact, the delta heat of formation at standard state is negative 285.8 kilojoules per mole. Okay, of that stuff that's being formed, and a mole is 18 grams. Of course, you know that. Anyway, so it's exothermic. And that means energy is being released. So these are the reactants. And this is the product. So today I'm going to be doing energy graphs, or we call them energy diagrams. So let's make a graph out of this bad boy. Here we go. And the graph is on page 532, but let me make heads and tails of it. The y-axis is energy. And it gets greater as you go up. And that's the course of the reaction as the action progresses. On the y-axis, on the x-axis. So now, where do we start? Well, we start with high energy reactants because they're in a gaseous state. I've already told you that. So we're going to put that up here fairly high. Well, let's just put it right here. Fairly high on the energy scale. And then what about the products? Well, isn't this releasing energy? Isn't delta H negative? So that means that the products will be energy that's down here. So this represents the reactants. This represents the products. Now what happens? Well, if you take a look at the graph on page 532, it looks like this. And this right here is called capital E, subscript A. It's called activation energy. And that's the energy that you have to provide to break the bonds. Do you guys see right here, there's an H and an H. They're bonded together. Right here, there is a O and an O that are bonded together. And you have to supply a certain amount of energy called activation energy to get it up there to the point where the rock is rolling down the hill, where it has enough energy to break these bonds. And now we have separate species that are really excited, that want to combine together. Now, what is it that, why do we have to put that activation energy in there? Well, when this thing is bonded together, there's an electron cloud. There's an electron cloud around this atom. And there's an electron cloud around that atom. And they repel one another. Sorry. The electrons, they're sharing electron clouds. They're overlapping. They're overlapping. Yes, they're sharing electrons. And so you have to provide energy to break that bond right there. Okay, that's activation energy. Let's read the definition. Activation energy is the minimum energy required to transform the reactants into an activated complex. So what's an activated complex? Go to the next page. It's a transitional structure. It's only there temporarily. That results from an effective collision. Remember, you have to have effective collisions and enough energy to break bonds to make different molecules. That's called the collision theory. You have to have an effective collision that persists while old bonds are breaking and new bonds are forming. What are the new bonds that are going to form? This hydrogen with that oxygen, this hydrogen with that oxygen. And when they form, you're going to get two H2O. Because there's going to be a bunch of oxygens floating around. Well, we got two H's, that's right. We got two H's. And so we got H and H combining with O and O. That makes sense. Okay, so a couple of these H's will combine with that O. A couple of these H's will combine with that O. And we got two water molecules. Okay? Now, so the activation energy is that. Now let me tell you about another thing that's on this diagram. And that is delta E. Delta E is always the difference between this and this. Delta means change in the overall energy. Are we going down? Yes, we are. We're reducing energy. Why? Because it's exothermic overall. It's exothermic overall, which means that the reactions have higher energy than the products. If it were endothermic, if we were coming back this direction in the opposite direction, we would say this. That's reactive. And that would be this stuff would be the reactant, and this would become the product. On a reverse reaction of what I just said. Now the question is delta E going to be the same? Is the difference between the starting energy and the finishing energy still that same amount of energy? Yes, it is. Except which way is the arrow going to go? The arrow's going to go up. This is where we're starting, and this is where we're finishing. When the arrow goes up, you're getting higher energy. You're taking energy in. It's positive. It is endothermic. And so when you go from this way back to that way, is this through an electrolysis? Are we putting electricity in to make it drive that direction? And when we go from here over to there, what are we putting in? We're putting in the heat of a match. Okay, but just a little bit, just enough for the activation energy. And after that, it runs spontaneously and it releases energy. But this doesn't. You got to put energy in to get it started. And then the energy overall, the energy change is positive. So it's going to be delta E is the same either way. Let's say that it starts out at 50 joules and ends up at 20 joules. That would be 30 joules different. In the reverse, by the way, it would be products minus reactants. So going forward, it would be, what do I say, 20 and 50 joules of energy, 20 let's say kilojoules of energy. Okay, so going downhill like that, it's always products minus reactants. And so 20 minus 50 is going to be negative 30 kilojoules per mole. And that would be delta E, because you're going down. You're releasing energy, exothermic overall. But endothermic, you have to put energy in. I mean, overall, the whole equation, you got to put energy in. You got to keep putting energy in. So delta E is also 30, but it's products minus reactants. Now this time, 50 is the product and 20 is the reactant. So 50 minus 20 is positive 30 kilojoules per mole. What are you telling me? I'm telling you that delta E on these equations, where you're running it forward or whether you're running it backward, is always going to be the same. In this case, it's 30. In this case, it's 30. Forward is 30 negative. Backward is 30 positive. Forward is exothermic overall. Backward is endothermic overall. And there's one more thing I didn't tell you about. I told you about activation energy to get it started going forward. Now, I'd like to know, what is activation energy to get it started in reverse? Well, you got to start with the reactant. That's in reverse. This is the reactant. And you got to go all the way up to the activated complex, to the top of the activated complex. And so in this case, let's suppose this is up here at 70 kilojoules. So you got to go from 20 all the way up to 70. You got to put in 50 kilojoules per mole to activate this thing in reverse. Whereas forward, you put in, let's see, 50, you put in 20. It's positive because you got to put it in to get it started. It's endothermic initially, exothermic later. Going backward, it's endothermic initially and a big endothermic. You got to put in not just 20 kilojoules per mole, but you got to put in 50 kilojoules per mole to get it from this point of 20 all the way up to 70. And this, going forward, you went from 50 up to 70, and then it rolled down to 20. So the activation energy was 20, positive. And the overall energy, the difference between here and there, is 30, and it's negative because it's going downhill and it's releasing. Whereas going backward, you start out at 20, and you're going to go all the way up to 70, so it's 50 kilojoules per mole activation energy, and we call that EA prime, meaning going backwards. This is EA, and EA prime is 50. It's positive. Activation energy is always positive. Putting it in. The overall reaction can either be negative or positive. Because you're either going downhill, see, the arrow going down, overall energy change, delta energy change, or you're going uphill. Now that was longer than you had hoped. You have a nice day. We'll pick up there.